In section 6.8, we're going to be working with logarithms. So let's revisit the definition of the natural log as we defined it earlier in the textbook. And we just have this theorem 6.4, which is just reminding us of the different algebraic properties of logs, and then here is our integral of 1 over x and how that equals the natural log of the absolute value of x, and then what our domain and range are. So in example 1, let's just go ahead and compute this integral. I'm going to use substitution. I'm going to let u equal x squared plus 9. That would mean that du equals 2x dx, and then 1/2 du is going to be equal to x dx. That means my x dx right here. I'm going to substitute 1/2 du in for it, so I'll go ahead and write that down. Alright, I went ahead and got my limits. When x is 4, just plug that in. You'll get a 25 for your upper limit and 9 for your lower limit. Carrying on with this further, I'm going to get 1/2 natural log of the absolute value of u, evaluated from 25 to 9. Plugging that in, I'll get 1/2 natural log of 25 minus natural log of 9. And using my log properties, I can write this as 1/2 natural log 25 over 9. Using that power rule, I'm going to write that as natural log of, and it will be each of these to the 1/2 power, so that will just be 5 over 3. And that gets it for example 1. This next little bit defines what a natural log is exactly. So this is the definition of both an exponential function and a natural log. Here is exactly what e equals. And then we come down here to some algebraic properties for e, just reminding you of those and reminding you of our derivative and integral rules for exponents. So let's play with example 2. I believe I'm going to use substitution again. Let u equal, how about 1 plus e to the x? That would lead to du equals e to the x dx. So I'm going to substitute e to the x dx. I'm going to write a u for that. So let me write that down. Alright, this will give me natural log of the absolute value of u plus c. I'll replace that with what u is, which is 1 plus e to the x plus c. I note that 1 plus e to the x is always positive, therefore we can drop the absolute value symbols because they're unnecessary, and there we have it. Next, we're looking at exponential functions with different bases, and here we have just the definition of some constant other than 1 raised to the x, and how another way to represent that. And using that, then I can derive the derivative for logs of other bases and the derivative of some constant raised to some function, and also have the integral for that as well. So let's see what we can do with that summary. If I look at a, I will probably use substitution again, and I will let u equal x squared. So if u is x squared, du is 2x dx, and then that gives me 1/2 du equals x dx. So I'll be substituting for x dx. I'm going to substitute this 1/2 du. So if I write that down, I'm going to have integral of 3 to the u 1/2 du. That 1/2 can go out front. It'll look a little better. So 1/2 integral of 3 to the u du. I believe that fits this one right here, and that means I'll have 1/2 times 1 over the natural log of whatever that base was, and that base is 3, and then 3 to the u plus c, and then I'll back substitute what my u is, and I get 1/2. I'll just write 2 natural log 3, probably look a little better, times 3 to the x squared plus c. Alright, I'm going to use substitution on this next one again, and I am going to let u equal that, let u equal negative x to the 1/2. That means that du will equal negative 1/2 x to the negative 1/2 dx. Moving this constant over, negative 2 du is 1 over square root x dx. I'll be replacing this 1 over x dx with this negative 2 du. That worked out nicely, didn't it? Let me get my limits of integration. Alright, for x equal to 4, just plug that in. Square root of 4 is 2, so that would be a negative 2, and likewise for the 1. That's how I got that. This negative 2 is a constant, so he'll go out front, and it will look something like negative 2, integral of negative 2, negative 1, 6 to the u du. Well, that's just this guy again. So I'll write down what I've got, and that would be the negative 2, and then it'll be 1 over natural log of 6, because it's 1 over the natural log of my base, times 6 to the u, and then evaluated from negative 2 to negative 1. So I'm going to be plugging those in and see what I get. Okay, plugging in those limits of integration, this would be 1 over 36, and this would be 1 over 6. Get you a common denominator, squish those together, and when you work that out, you'll end up with that right there. Alright, the point of this last example is to get you to realize that this is x raised to some function, and the general power rule says that this works for real numbers p, and this power rule is only for real numbers p. 2x is not a real number p. So we've got to be really careful and make sure that we don't use the general power rule when it's not appropriate, because in our theorem this only works for real numbers p. So instead we'll just maneuver it a little bit, and we'll use this definition of exponential functions. It'll come in handy, because I can write f of x equals x to the 2x. I could write that as e, and then wherever there's an x, I'm going to write this 2x natural log of my base, which is x. So next I'm going to take the derivative of this, so f prime of x. I'm going to use the chain rule. The chain rule says take the derivative of the outside, which is the e, leave the inside alone, times the derivative of the inside. So it'll just be e 2x natural log of x times the derivative of this 2x natural log of x. For that I'll use the product rule. So derivative of the first, that would be a 2, leave the second one alone, plus leave the first one alone, times the derivative of the second, which would be 1 over x. Then putting all of that together, I've got e to the 2x natural log of x. And then this just will look a little bit better if I go ahead and say, how about if I pull out the 2, just call it a natural log of x plus 1. And then once I've got that, I can say, well, this thing really is just x to the 2x, and then I like my 2 out front, natural log of x plus 1. Alright, looking good. Alright, if you have any questions about that, see me in the Collaborate. And that is the end of 6.8. That was a pretty nice little section.